that makes it easy.
Go on.
Another
You reckon you can pull that out with your hand?
Maybe. Done.
It's hot?
Let's get solid.
Big boy Todd.
He's cheating. Is he supposed to just go like
Yeah, wait until you pull up top. Can you pull it up?
No, that won't work.
What about if you use the hammer top?
Yeah.
Show us how you use that.
But because now it's so long, you need a block over there to help it.
Just use it first.
You want a block? Hold on.
Okay.
Okay.
Because it's so long, it will be more difficult to pull it out.
Looks like
Crazy.
a bed to the night.
Oh, that's gonna go wrong. Oh, just use that wrong.
Just use your hand.
just sitting on it with your legs between it and yanking.
Just what?
Yeah.
Are you kidding us? This is golden.
I'm getting it. Yeah.
Yo, how's it even doing that? That's
actually insane. That's insane.
Physics.
There you go.
That's it.
Now show us how it's done.
That's gonna fly. Oh, okay.
Easy leverage. That's what we're doing.
What just happened?
He pulled the...
It's so warm now as well.
That's too right.
Thanks for your demonstrations. And when we're doing talk, we're going to write it with the curly T. It's kind of like a backwards J with a pie hat on it, kind of thing.
It's warm.
That's cool.
Which is the Greek letter Tor, and the reason why we're going to do that is because that's the symbol we're going to use for torque when we're doing calculations. Torque is a twist. It's a rotating force kind of thing. It's different to a force though, but we can link the torque to force. We've got an equation that links torque to force, which is what Todd was so ably demonstrating for us, that torque is equal to force cross. I want to put an R there for radius, but on your formula sheet,
Where did you get that?
Oh, it's just right here.
On your formula sheet, it's torque equals force cross distance. In year 13, it turns into force cross radius, and so it's better to learn it like that, but it's going to look like that this year. So either of those, same thing. And the difference between torque and... Do you remember from last time we looked at work? Right.
Yep.
Work is force times distance. What's the difference between torque and work?
Doesn't work like the energy.
Does torque have direction?
Do something.
Work is like both.
Put into something.
It's torque vector.
Work,
Not like energy.
work is energy, yeah, good. But they're the same equation,
So they're just
right?
same.
Same equation.
The same thing. Working and torque.
Oh,
No,
no.
the dot
Work
is
is
exactly the
direction.
vector.
Work is direction.
Work is a direction.
No, torque
Is
is
that what the
direction.
dot means? Does that mean
said
it's a
that.
It
vector?
means it's a vector.
The dot tells us about the direction of these two quantities.
Oh, they go in the same direction. So force and distance are not in the same direction.
They're at, what does that X mean?
Right angles.
At right angles to each other. That the radius and the force must be at right angles to each other.
What the hell?
Yeah.
It's true.
That's weird.
Oh, that makes sense.
Radius. Yeah. Because the radius is going like that out from centre and you're pulling like that.
Time lapse.
Two different kind of meanings. It's either the radius or the distance from the pivot or the fulcrum. The centre of rotation. So what's this torque thing? That's the torque, right? What's that measured in?
Newtons per meter.
Where's the per?
No per.
There's no per.
That's right.
Newton meters.
Newton. But it's not going to be meters. It is Newton meters. Damn. That's complicated.
Newton meters.
And so we can use torques to solve problems. Like, for instance, we had the hammer problem that Todd was running into, that he tried pretty hard to pull that nail out with his hand. So how did the hammer help?
I guess we never know.
Guess what?
That's a story for another day. Nah, I can't even see it. Oh, okay, it is hanging. It is actually.
And so, what have we got happening? We've got Todd.
F Todd.
F Todd that way,
Damn.
and we've got the distance from the pivot point to the force, the R Todd, like that. So Todd's doing a force and he's creating a torque, and Todd's force is probably something like about 20 kilograms, 200 newtons, let's say. And the distance was about 0.3 metres. So torque that Todd was producing might be around about 200 times 0.3, which is around about equal to 60, right? But that same torque has to be transferred through to here. That same torque must be acting down here, and the distance from the pivot point to where the nail is, that's more like 5 centimetres. So we've got about 5 centimetres there. And so how much was the force? We know that torque is equal to force cross radius, and so force must be torque over radius. Force must be 60 over 0.05, round about 1200 newtons, like about 120, as if Todd was pulling that nail with the force required to lift 120 kilograms of mass. And so what the hammer is doing is saying that whatever torque Todd creates by pulling on the handle, that same torque must be existing on the nail, and so that means that because the distance here is much less than the distance here, we get a much greater force, 1200 newtons from only pulling with 200 newtons. Or amplified your force.